I'm Johan. I'm Swedish, but I currently live and work in the UK. I'm a maintainer of various open source projects. I've contributed to the Go standard library, and I run a blog writing mainly about Go and gRPC. This is my first visit to Moskva, and I'm very happy to be here. And I'm here today to give an introduction to WebAssembly with Go. Oops. Today, we will learn what WebAssembly is, how to use it with Go, show what's possible today, and look at what will be possible tomorrow. So why WebAssembly? So we like to write Go, and we'd also like to be able to write websites. And normally, that means using JavaScript, NPM, etc. But we hate using JavaScript and NPM, so that's why we're using Go instead, right? And with WebAssembly, we can instead use Go for both the front end and the back end. You could write the next Kontakte in Go. So what is WebAssembly? It's a web standard binary instruction format, like x86, but developed for the web by the World Wide Web Consortium, with representatives from all 4 major browsers, and with community contributions. It grew out of the ASM.js project, which proved that languages like C and C++ could be transpiled to JavaScript and run in the browser. Google developed the NaCl native client, but it was never implemented by any other browsers. And instead, a joint effort was started to develop something new. WebAssembly was designed to be fast to interpret, fast to execute, and of course, secure to run. Where can we run it? It's been supported in Chrome, Firefox, Safari, and Edge since late 2017, with every modern browser that matters now supporting it. A smattering of runtimes, written in a variety of languages, have also appeared, with Wagon and Life being the larger Go-based WebAssembly runtime projects. The prevalence of runtimes means that WebAssembly isn't just a language for the web anymore, but runnable anywhere the runtimes can run. We might even end up with a bare metal chip implementing WebAssembly at some point. All of that is still some way off, though, and today we will focus on WebAssembly in the browser. How can we interact with the world from WebAssembly? WebAssembly in browsers ship with a JavaScript interface to access existing browser API tasks such as DOM manipulation, making network calls, and using WebGL, to name a few. We'll take a look at exactly how that works with Go a bit later on. Another interesting platform interface is the recently announced WebAssembly System Interface, aka WASI. Initially designed by Mozilla and Fastly, it's being standardized by a WebAssembly working group. It's designed to be used when compiling WebAssembly for running outside of the browser, and provides a Syscall-like interface to system features like files and network sockets. It's currently still in development, but provisional support for WASI is present in Fastly's WebAssembly runtime Lucent and Mozilla's WASMtime. But what does all of this have to do with Go? First, let's take a step back. Go4JS is a tool that has allowed Go in the browsers since 2015 already. It's the tool for compiling Go to JavaScript, written by Richard Musial, aka Nilans. It supports most of the standard library, and there are many community bindings for existing web technologies such as WebSockets, local storage, and other things. It's very easy to use, and as this graphic shows here, you simply provide your main.go file to Go4JS build, and it spits out the JavaScript file that you can load in your HTML. It remains the most mature way of running Go in the browser and is used by projects such as Perkeep. What about WebAssembly? In early 2017, Brad Fitzpatrick opened a tracking issue for implementing WebAssembly target in Go. The conversation quickly took off, but no real consensus was found for the best way to implement it in the existing compiler codebase. The WebAssembly spec is notably missing the Go-to keyword, which makes implementing control flow harder and is hindered initial work. However, by November, Richard Musial, the author of Go4JS, announced that he had started working on implementing a WebAssembly target for the Go compiler. And it shipped in Go 1.11 roughly 9 months later. Richard deserves a lot of credit for his amazing work in bringing this novel architecture to Go on his own in his spare time. And Go 1.11 shipped with experimental WebAssembly support, which means that it doesn't have the same backward compatibility guarantees as the rest of the standard library. And this is still true today, with no clear plan on stabilization. You can expect breaking changes to still happen between releases, and so be careful when considering using it for production code. It supports most of the standard library, including NetHTTP client requests, which we'll see a little bit more about later. Currently, only the JavaScript system interface is implemented, but there are plans to implement WASI in future Go releases, hopefully as early as 1.14. And that would mean you could run it in a runtime such as Lucent or Wasmtime, and maybe even on Fastly's Edge network. As this graphic shows, compiling Go code for WebAssembly is as easy as any other C-Go-free cross-compilation. You simply specify the Go OS and Go Arch environment variables when building. And let's briefly discuss the elephant in the room here. As we'll see soon, it produces very large binaries, and there's a few reasons for that. Small binary size has never been a design goal of Go, and you've probably yourself noticed that large Go code bases tend to produce large binaries. The CockroachDB binary is 123 megabytes large, unstripped. The heavy Go runtime, the garbage collector, and difficulties of performing dead code elimination in a language that has a runtime reflection all add to the problem. The image we're looking at here is the weight of each package contents in a Hello World binary built for Linux/AMD64, and it adds up to 1.2 megabytes, a simple Hello World binary. And as you can see, most of that is taken up with just the runtime. There's a little bit of reflect and FIMT in there. Just importing FIMT adds about 200 kilobytes to your file. And furthermore, we discussed earlier that WebAssembly doesn't have a go-to instruction, and this leads to larger output for the same functionality. But later on, we will see what we can do about file size. So how can we use WebAssembly with Go? First, there's a little bit of server setup necessary, mostly to set the correct content type. Browsers will not parse and run WebAssembly files unless they have the correct content type set. The Go standard library comes with a very important file that ties your WebAssembly file to the browser APIs. This is the wasm_exec.js, which is mandatory. You must include this in your release. Make sure you're using the same version of this file as the version of the compiler that you use to compile the WebAssembly. This is most easily accomplished by copying directly from Go root when building, and I'll show an example of how to do that later. wasm_exec.html is an example of how to load WebAssembly and expects a test.wasm file. They're both included in the standard Go releases, and I've included a little server here that serves from the file system and sets the content type appropriately for files with the extension .wasm. But enough theory, let's take it for a spin. So I'm going to show you some examples from my example repository, and if you have your laptops with you, I see a single laptop out there. If you like, you have about 5 seconds now where you can clone the repo, and it's gone. Let's jump straight in. So what I wanted to show you first here is a simple Hello World binary, and as you can see, this looks like a completely normal Hello World. All of this is just standard bog standard Go. We use the FIMT package. We call printline Hello World. The only thing that you may notice here, which is a little bit strange, is this build tag at the top. And the build tag, in this case, is used to make sure that this only builds when you're compiling with the Go OS JS and Go Arch WASM. So in this case, it's actually not really necessary. But I wanted to show you here what it looks like when you use the build tag. So basically, if you try to compile this package for Linux AMD64, it just won't build, which is good when you're using syscalls, which we will see a little bit later. So if we build this now, you're going to see what I talked about before. You call the Go build using the Go OS JS and Go Arch WASM. We're outputting it to HTML directory in this case, and we're obviously giving it the WASM, the main file. And then the important part here is that you make sure to copy wasm exec from the same version of Go that you use to build the file. And as you can see here, just using a go root will always give you the root of the current Go binary. So this is a nice, simple one-liner you can use to make sure that you get the correct version of wasm exec. And in this case, we're also using wasm_exec.html and just renaming it to index.html. This is just to make this demo a little bit easier to run. As you can see, there's hardly any modifications of the standard library files here. So if we run main.go now, the main.go file that I'm going to run here is just a file server that serves the HTML directory. And then we can open Firefox. And I wanted to show the network tab here so we can see what the size of the files are. And this file is 2.16 megabytes large, which is completely unacceptable for something that just prints hello world, right? Bear with me. So if we go to the console here, the standard out in normal Go binary will map to the console in the browser for a WebAssembly file. So if we press run here, we get output hello world to the console. It's working. Live demos. OK. But this is not that interesting. In order to access browser APIs from WebAssembly, such as for manipulating the DOM, we have the syscall/js package. This is not meant to be used by all Gophers writing WebAssembly code and should only be necessary when you're working with the browser APIs directly. It's based on the interface Richard developed for Gopher.js with its own little adaptations because of the different runtime. If you've used Gopher.js interface before, it will look very familiar. It supports sending callbacks to JavaScript, which is essential to use certain JavaScript browser APIs. And something important to note is that whenever you use the syscall.js interface, all the data you pass to JavaScript has to be copied, as WebAssembly and JavaScript don't yet have a way to share memory. As such, data transfer between the two domains should be minimized for greatest performance. What you see here is a simple example of a JavaScript snippet translated to syscall.js calls. And as you can see, this is basically writing JavaScript directly in Go, completely stringly typed. It's not so nice. And this is not why we use Go. But let's take a quick look at how we can use JavaScript from Go. So we're back here again. In this demo, because we are importing syscall/js, it is paramount that you include the build tag, because this just won't build for any other platform. So in this case, we have the build tag here. We have a package main again. We import syscall.js. And then the stuff down here is loosely translated straight from JavaScript. So we're getting the document in order to be able to manipulate the DOM. We're finding a target div, in this case, which we're going to be inserting ourselves. We'll look at that in a second. With that div, we will then append a node to it later, which we have previously created. So this is a new div that we created straight on the document. We're setting the inner text to hello world. And if you've been following along, what's going to happen here is that a hello world string is going to be printed inside of the web browser rather than to the console, because no one looks at the console. And we want our people to be able to use our websites without having to use the browser console. So let's build that. And again, this is almost exactly the same. We run go build. We copy the necessary files. And then we've got a little bit of sed magic here, which, if you remember from the previous demo, there's a run button. This one finds the button. It replaces the end tag of the button with an end tag of a button and a div just below it. And we give the ID of this div target so that in the document here, when we're looking for the target div, it exists. And then we can run main.go. OK, so you've got the page here. Let's see what the size of this file is. So this file is actually 1.23 megabytes. And can anyone tell me why this is almost half the size? There's no FMT. He's been listening. Very good. FMT adds about a megabyte to your file size at the moment. It's not great. OK, so if we run this, as you can see, now we have hello world straight into our DOM here. Oh, wow, I shouldn't have done that. Let's not do that. And this is obviously much nicer than just using the browser console itself. But again, this is still not a web app. So let's take another step back. What about web frameworks? Vecti has been around on the web scene for a while and was purpose-written for creating Go apps with Gopher.js. It was created by Steven Gutekunst and Richard Musial and recently underwent a rewrite to make it compatible with WebAssembly. It uses a React-like interface with struct declaring styling, functionality, and composition. It's currently under the Gopher.js GitHub org, but don't let that fool you. It's maybe moved to its own org in the future, and it works just fine for both Gopher.js and WebAssembly. Let's take a look at a quick example. So we've got a Vecti file here, and the first thing you'll notice is that there is no build tag in this file. And indeed, it's not necessary here, because technically you can use Vecti both with Gopher.js and WebAssembly. So this file will compile for both Gopher.js and WebAssembly. And if you try to compile it for Linux AMD64, it will probably not build at all. But you could potentially add a build tag here, just saying it should be either WebAssembly or a Gopher.js. But we don't care so much. In this case, what we want this to be is just a normal Go program. And indeed, it just looks like a normal Go program, right? We have no syscall imports. We're importing vecti here, obviously, which is the framework that we're going to be using. We have a main file, main function, and we can set the title of the web page. And then what we've got here is just a render body and nothing else. So obviously, this function will block, and there isn't anything obvious to show how to render this body. So obviously, all of this is going to be tied to this page view type. And if you're familiar with React, then this is going to look very very common indeed, because we've defined a render function on this page view type. And we also have a little bit of initial state here on the page view type. The page view embeds vecti.core, and it defines some state here. And then it defines render, which is declaring how this component should be rendered. And as you can see here, we have markup like the body, we have the div, and inside the div, we can define specific markup for this div, and inside that, the div again, we can define a text area. And so there's a little bit of HTML inside of Go here, but actually it's really nice to write. It's all nicely typed, so obviously you can add a property here. This is an empty interface, but for example, when you're working with input events, you take a function that you give it a function that takes a vecti.event, and you have properties on the event. So rather than working with empty interfaces all everywhere, Vecti tries to do as much as possible strictly typed functions. So what we're doing in this text area here is obviously we're defining some some CSS styling, and then we have an input event handler. So whenever there's an input event on the text area, we update, we get the value of the text area, and we call re-render on ourselves recursively. So, and then we have the initial state here, which is that was created at the top here. And then at the bottom here, we have another type. So obviously, this is a really nice example of composition. And of course, this type also embeds vecti.core. It has some state on it, and it defines render. So this shows how you can compose different types into a hierarchy of types so that you have different parts of the document implemented by different structs, and it separates the logic nicely from each other. And it can all kind of be composed in a single file like that. And what this type does is grab the input. It will give it to this markdown render called Black Friday, which outputs you some unsafe HTML, will then sanitize the HTML, and then print it straight back into the element. So the representation of the markdown in on the website is going to be the rendered markdown. So let's take a look at what that looks like. In this case, so let me quickly show you the index.html as well. The previous examples that we've been looking at all use a run button to trigger the start of the WebAssembly execution. But obviously, when we're working with a web framework, we want it to start as soon as the WebAssembly has finished loading. So in this case, we have a custom index.html file, which just loads the module and then immediately runs it here. And it doesn't wait for you to press a button or anything, which is ideal in this case. So let's open the browser again. And if we reload this page, first of all, we can see, OK, 3.6 megabytes, not too bad. not too bad, not too good. No, I'm trying to make a Chernobyl reference here. It worked well in the test. Anyway, so what you can see here is on the left side, we have some markdown, and on the right side, we have an editor. And what happens if we start typing things in here? List. Oh, OK, it updates automatically. And so this is a really nice, really simple example of how you can write something quite powerful with so few lines of Go, right? What we did there is like literally 50 lines of Go, and you have an actually powerful example that it imports some third-party markdown renderer, and it all just works. It just renders it in the browser like that. So it really shows, I think, the strength of Vecti to make it look like real Go and still make it really powerful without being too verbose or having to use empty interfaces or whatever you end up with in some other languages. OK, but Vecti is not the only WebAssembly Go framework. Vugu is a relatively new entrant to the Go framework scene, written by Brad Peabody. Where Vecti is a framework inspired by React, Vugo takes a lot of cues from the Vue JavaScript framework, as is evident by its in-markup logic and bindings. It uses a custom file format that is a superset of HTML, coupled with a code generator that produces the final code that gets compiled. It has put a lot of effort into the development environment, with features like automatic rebuilds and reloading on code changes. You can try it out in the online playground, and let's take a quick look at a demo. So when you're working with Vugo, we don't end up working with a Go file. We use this concept of a Vugo file. And as you can see, we have the markup up here, which is basically HTML. And then we have all of the Go code encapsulated in this script tag. If I change this to HTML, then you can see that this just looks like normal HTML, right? We have a div here. And then we have this attributes, vg.if, which if you've ever worked with Vue before, then you will feel right at home with these things. It evaluates, as if Go, the statement here, and whether if it's true, that it will show the div, and if it's false, then it will not show the div. So these two things ideally should not be true at the same time. So for example, when the app is loading, then it will show this, and then when it has some data, it will show this, and it won't be loading anymore. They're not logically mutually exclusive, but that's up to your application to make sure that they are. And then inside here, we have something quite interesting as well, a for loop. And this data.bpi.bpi, which we can see down here, is a map from string to struct. And so this for loop here loops over a map, not just a list, a map. So you can access both the key and the value of the map and print it out using spans in this case. And then down here, most interesting of all, I think, is the button handler. So we have a @click, which is assigned to a function called handleClick, and this function is going to fetch the Bitcoin price index. So if we now switch this back to Go again, inside this script tag, as you can see, this is all just Go. There's no build tags here. There's no syscall.js imports. We have some types here. We have a root data type, which is what you kind of anchor all of your types to. And then we have a type here, which is used to marshal some JSON. And then we have the handleClick function, which, because it mustn't block the kind of main rendering thread, starts running in a Go routine. We have some locks here in order to update the root data. So you can set, when you click the button, we set loading to true, obviously, because it's loading. And then, so this is quite cool, I think. You can call something like HTTP GET from WebAssembly. And how does that work, right? Because WebAssembly doesn't run on the system. So what WebAssembly does under the hood is go to the browser fetch API, and it calls a fetch function it translates like the properties on the request. In this case, we're using the shorthand, which creates a request for you, but it supports a lot of things like cancellation, context cancellation. It supports streaming request bodies. It supports streaming request responses, etc. So the fact that HTTP GET just works in WebAssembly, I think, is really cool. But other than that, this looks like normal Go, right? We're working with, we mustn't forget to close their body, of course, because we don't want to lose any file descriptors. And then we're just using JSON.decode. We're printing some errors, returning whatever. And if everything is happy, then we update the state. So in this, because this is a .vugo code, you don't just run go build. When you use Vugo, you use a tool called VugoGen. So if I run make Vugo here, you'll see that we're running something called VugoGen. And in this case, I'm kind of bastardizing the development environment a little bit with Vugo for the purposes of making it look a lot more similar to the previous examples. VugoGen is normally not invoked manually like this. Anusha had a nice example of where you can start a web server and just say, this is my root directory, update it whenever the file changes. And that's a nice way of developing with Vugo. But in this case, I wanted to show you what it would look like comparatively to the other demos. So we run VugoGen on a directory. VugoGen spits out the root.go, the main.go, and index.html, I think, in this case. And so you don't touch those files, you just touch root.vugo. And then you can run go build on that directory, and obviously that will include the Go files. You can then copy the index.html over to your directory or whatever, and don't forget to copy wasm_exec.js or nothing will work. So let's take a look at what that looks like. And now we have to pray to the demigods that the Wi-Fi is going to be working. Let's first take a look at the size of the files. So in this case, the size of the file balloons to 10.15 megabytes. And this is not Vugu's fault. This is because it's importing HTTP, NetHTTP. So the funny thing about NetHTTP in WebAssembly and in Go in general is that whenever you use NetHTTP, there's no way for Go to tell generally whether you are just using it as a client or as a server. So because NetHTTP has an entire HTTP2 server stack included in its dependency tree, you end up including an entire HTTP1 and HTTP2 server stack in your WebAssembly file, and it compiles, but it can't run. It compiles just fine, but it produces 10 megabytes of data, so it's not that great. But again, we will come back to file size in a moment. Let's just take a look at what happens here. So if I press this button, what I'm expecting to happen is that we will get a little loading indicator, and then we should wait for a moment while the CoinDesk API responds to our network request. Bam! And actually faster than I tested it yesterday. And here we have the Bitcoin price. It's time to sell, I think. And so that's the Vugu demo. Okay, so we've seen a few demos, but what can we do about file size? All the demos we looked at are served uncompressed, and we can get a quick win by using compression, and GSIP compression is usually so quick that you can do it directly in the handler. And you can get something like a 70% easy win just by using GSIP. Brotli brings you another few percent down, and if you use a CDN for the static files, they will add compression automatically and serve the best available compressed file to your client based on what they can support. And they will also ensure the files are available at data centers all over the globe, which will help latency and make download speeds faster. The brilliant Dave Brophy put together a package called Go, which will take your Go files and upload them to a CDN and then give you a URL on which you can serve the WASM. So feel free to try that out for your own demos. We saw at the start that the standard library is somewhat responsible for the compiled file size, and we can in part help with the file size by avoiding certain imports, such as FIMT. But let's be honest, we don't want to have to do that. We like writing Go because it's simple, right? We don't want to have to use Go. Let me, before we continue, because we have a little bit of extra time, I want to just show you how big difference it makes when you use GSIP to serving. So this demo was 10 megabytes large, and if I run this server with the -gzip flag, I'm hoping this still works now. I haven't tested this since I last ran the demo. You can see that the file size shrinks down to 2.77 megabytes. So that is a very, very good reduction in file size. And actually, something I did want to say was that the official Vugu website is written in Vugu. They're dog feeding their own stuff, which is cool. So there are some websites that are already using it for production, which is really cool. Although it's kind of a contrived example, because obviously they want to show that they can run their own stuff. OK, but what can we do about file size? Maybe something else. Enter TinyGo. It was created by Eike van Latem primarily for using Go on microcontrollers. It took the Go WebAssembly community by storm when the first WebAssembly demo showed that it could produce tiny outputs. It's built on the LLVM stack, and it's still very early days. A lot of things will be broken if you try to use it today, but it's a very exciting project to keep an eye on. It gets better with every release, and we're hoping to have it able to run Vecti or Vugu websites eventually. And let's take a quick look at an example of what TinyGo can do. So the first thing I want to do is show you the same demo that we're going to be using with TinyGo with a normal Go compiler. So we're going to build the Canvas demo, which I'm not going to show you the code for because you will see in a moment why. A Canvas demo is developed by a gentleman called Louis Figueiredo. He's got some really cool kind of graphical demos on his GitHub. So this, sorry, let's reload this and just take a look at what the file size is. The file size for this file is 2.29 megabytes. Not great, not terrible, that's the one. This is just a cool graphical demo using the canvas to draw some dots, and you can play around with this, add more dots. More dots, sorry. And you have a nice FPS counter at the top. And indeed, you have the source of this is all in the background here, so it's kind of nice. You can just kind of scroll through it, see. But okay, so don't use this for your inspiration to write your own websites, because this is all written using syscall.js, and it's absolutely horrible to develop against. The idea of syscall.js is that you'll write wrappers around it, but Louis wanted to write it using just standard library imports, which he has accomplished, and he's got a few of these cool graphical demos. Really talented guy. Anyway, that's the standard library compiled version. If we go back and we build this with TinyGo instead, using the TinyGo, shoot, I want you to see what the command is. Using the TinyGo Docker container, you don't have to install TinyGo to build something with TinyGo. The point I wanted to make here, my Wasm experiments repo contains a few examples of how you can build with TinyGo. And in this case, we run the container, we mount our local directory, we run TinyGo build, make sure to copy Wasm exec. The Wasm exec file for TinyGo is a little bit different from the one in the standard library. So again, make sure you're using the same version of the compiler and the same version of Wasm exec. And then we just copy the index.html. Again, this index.html is going to be one that executes immediately. But let's see, how large is the file? Reload the page. And 99 kilobytes. Thank you. Thank you. Yeah, so this is a really cool example of what TinyGo can do. But let me warn you, because if you run off and start trying to compile basically anything for WebAssembly with TinyGo, it's not going to work. TinyGo doesn't support the reflect package completely, which breaks like most of the standard library. But it does work for a lot of cool things. And obviously, TinyGo also works really well on microcontrollers. So if you've seen previous TinyGo talks about using it on microcontrollers, I can recommend you just try it for your Arduinos. You never have to write C again. OK, so as you can see, this still does all of the same stuff. So it's really impressive. But this is basically the most advanced demo that you can accomplish with TinyGo right now. A look to the future. Among the things planned for WebAssembly itself is a proposal to make it easier to interact with browser APIs directly from WebAssembly, instead of going via the JavaScript bridge. This should mean no copying of memory between the WebAssembly and JavaScript world when using browser APIs, and not having to worry about JavaScript callbacks and the like. Another feature on the horizon is WebAssembly threading, which is already available to testers in Chrome 70 and above. While Go is very good at concurrency and the current implementation supports Go routines, threading is not yet supported, and that might be a community contribution. The last thing I picked out is garbage collection, which is interesting to us Gophers for several reasons. What, you might say, we already have a garbage collector. But that's one of the reasons that compiled file sizes are so large. If we could exclude the garbage collector when compiling Go code for WebAssembly and instead rely on the garbage collector built into the WebAssembly runtime, we might be able to produce smaller binaries. This is one of the graphs produced by Todd Kuleza and Steve Francia based on the Go 2018 survey results. To me, this was the most interesting and surprising result of the entire survey. Let's remember for a moment that the WebAssembly support in the standard library is entirely the result of open source contributions, primarily read by Richard Musio. I'd like to think this graph will make the Go team invest some more resources into the development of the WebAssembly targets, but also to encourage you guys to bring your own ideas and contributions. The potential for WebAssembly is huge. In conclusion, we've looked at what WebAssembly is, how we can use it with Go, what's possible today, and what will be possible tomorrow. WebAssembly itself is going to continue to evolve with new features added over time, and it could not only replace JavaScript in the browser, but potentially realize the promise of truly portable system binaries. What will you build? Thank you.
Thank you, Johan. The gods of demos really loves you. All right, so here's a present for you, the matryoshka and the diploma.
Thank you.
All right. So you know the drill. Remember the questions.
Yes.
Do we have questions? Yeah.
Thanks for the presentation. I have like two questions. First is, does using WebAssembly and Go in this way raise some security issues? Let's say we can call HTTP GET. Is it okay? Is it used with like browser API or something else? Are there any possible vulnerabilities there? What do you think?
When using HTTP GET from within Go, you have to take the same kind of security precautions as you do when calling the fetch API from JavaScript. So you have to, when you're inside the JavaScript sandbox, you have to kind of worry about whether the server that you're communicating with has a CSRF protection enabled and things like that. All of those kind of concerns are still the same within Go. But from writing an application point of view, you're already inside of a sandbox. You basically do as much as you can because the Chrome sandbox is going to protect you, or the browser sandbox is going to protect you from doing stupid things.
So I can't call some bad code and fetch something bad.
You can obviously.
So this will be blocked, sorry, by the CSRF, like content origin policy.
It has this, yeah. So it has the same kind of guarantees that JavaScript. I mean, if you're importing a JavaScript library that downloads a Bitcoin miner and runs it in the browser, then you could do that in Go as well, and it might be a great idea. I haven't tried that myself. There's nothing stopping you from doing that as long as you manage to get loaded onto the website. But if you're the website developer and you're writing your own WebAssembly to host on your own websites, it's the same concerns as with JavaScript. The same guarantees and the same concerns.
Okay, thanks. Another one, if you don't mind. Did I get correctly that the TinyGo doesn't allow us to use FMT because of reflection or something else?
So that's a great question. TinyGo does support FMT. It does not support all of reflection yet. So it has its own kind of implementation of FMT. So FMT itself is not that useful when you're working with web applications, but it's very useful for kind of debugging microcontrollers, for example. Although often you will want to write to like a serial port or something like that, because most microcontrollers don't really have a way to kind of display stand it out anyway. But generally, I think FMT is supported, but reflection is not fully supported yet.
And sorry, just another one.
Yeah.
How to say this? Sorry, guys.
Is that it?
Okay, I'll come with it later.
Okay, no worries.
All right. I think we had another question there in the back, or no? All right, I have a question of my own while people are thinking. Have you heard of some projects that use WebAssembly not in the browser, but for example, to make use of a scripting language? For example, I would imagine that if you include WebAssembly like machine into your program, then you can use any language, like Go, for example, as a scripting language.
Yeah,
Is it
so
possible?
I briefly mentioned the two projects that implement the WebAssembly runtime in Go. There's a Wagon and there's Life, and I think they both support running standalone and running within another Go application. So what you could do is have your Go application import Wagon and say allow a user to upload their own WebAssembly code, and then you have that safe sandbox within which you can execute user code, and you might even have some RPC connections with the kind of main application or whatever. All of that thing is possible. I haven't actually done much with that myself because I'm more interested in running Go in the browser, but it's definitely possible.
Are they performant comparing to, I don't know, V8 or...
I think there have been benchmarks, and it will probably be comparable to running any other kind of sandbox inside of your application, but it's certainly quite a bit of an overhead compared to running native code. So if you're, Go has the plugin system, which you can use to dynamically load programs within your application, which will be faster than running WebAssembly, but you don't get that secure sandbox at the same time. So there's a certain overhead, but it's not that high.
Thank you. Alexei, you had a question?
Yeah, so you just mentioned the plugin package, and my question is about that. When you compile a Go code, what part of standard library is supported? Can you use unsafe package? Can you use plugin package? If yes, that opens a great possibilities.
Or great dangers. Yeah. Yes. For the standard Go, the Go target that's part of the GC compiler, I think most of the standard library is supported. I don't know if unsafe is supported. I imagine it's not, because it doesn't make any sense. Like you can have like pointers and stuff, but you can't. I don't know what else you can really do there. Let me know if you find out. I don't know myself. I haven't delved onto the kind of dark side of things. Actually, I kind of tend to stay away from the unsafe package, although I know some people really like using unsafe. But I think generally most packages are supported, and I think even interesting things like NetHTTP is supported.
Yeah, there's a question here. In the first row.
Can I say thanks to everyone, by the way, who stayed for the second WebAssembly talk of the day? It's really nice to have people listen.
Hi, my name is Ivan. Thank you so much for the presentation. And my question is, do you know any ways to use NPM packages in Go and WebAssembly? Because like JavaScript community is kind of big, and there are a lot of packages that we want to use without like re-implementing my own React or Angular or something like this. Do you know, are there any maybe tools to wrap these packages and use it in Go?
So I don't know if there's any kind of framework that wraps that whole process, but I'm pretty sure you can. You can. So you can first of all you can interpret the WebAssembly inside of Node. So then if you have Node where in the environment you have at the same time loaded some NPM packages, like you have Node modules or whatever, you can import those just like you would a normal JavaScript type. So where the examples that both me and Arusha were showing were all running in the browser, you access the global, and then you access the document, and then you call things like getElementById. If you were running in Node, then you would take the global and you would look at whatever you do to import a package. I think you can literally call global.call import or whatever. Like you can call the functions to import stuff that's in the same environment. So you can access NPM packages that way.
That's cool. Thank you so much.
Although I would stay away from the NPM tool frameworks. Sorry, the ecosystem myself. That's a personal preference.
Any more questions? I think I have the last.
Yeah.
So what I tried to say was, if we need some more than just 1-2 packages, and we have like two options. Either we use TinyGo and we can't use some of them because it doesn't fully support like reflection and stuff, or if we let's say we're building a real life application which is more than just FMT and something, how big can the binary get?
Yeah, that's a great question. And the question is right. Should we try and use TinyGo and try and compromise on all these things that it doesn't support, or should we try and use the standard Go library?
Exactly.
And the heavy weight that comes with that. And I would definitely say use the standard Go package right now, because TinyGo, it can't really do anything useful right now, and maybe never be able to rival the standard library packages, because it's a huge ordeal to kind of maintain a separate compiler that has to support the same thing that the standard compiler has. So at the moment, in my testing, and I've been using Gopher.js for quite a long time, which has the same problem. Actually, Gopher.js produces slightly smaller files. So if you want to write Go on the web, right now Gopher.js might be the best option. But if you want to use WebAssembly, which is really cool and faster than Gopher.js, probably, you want to use the standard Go compiler and try and use a CDN to make sure that the files are close to the user, that they're compressed. You get 80% compression. So when you import NetHTTP, yes, it adds 5 megabytes to your file size. But what you can do is you can load like a HTML page and then show like some spinning or whatever. Like personally, I don't think the file size is that big of a problem. Maybe that's my privilege having like high download speeds or whatever. I live in the UK. I don't know how big of a problem this is for your customer base. Whatever. Like you have to make that compromise yourself. Personally, I would use a standard library compiler.
Thanks a lot.
And that was the best question, by the way. Well done.
I have one more question.
Oh, yeah?
Can you tell us about the areas of development that's going on right now in WebAssembly?
Yeah, so the most interesting one is WASI, which I briefly mentioned at the start. Richard Musial, the creator of Gopher.js and the guy who implemented WebAssembly in the Go compiler, he's working together with a company called Fastly, who have developed this WebAssembly WASI runtime. They're really keen on getting Go running for WASI. So that means compiling Go applications for running inside of this sandbox, basically. And I think Fastly's end game is that they want to be able to deploy these applications on their edge network and be able to sell that. You can run your applications as if they're kind of lambdas, but inside of their edge network, so you have them locally distributed all over the world.
Cloudflare does this similar thing, right?
Cloudflare does a similar thing, but actually they use V8 workers. They don't use WASI, as far as I know. Mozilla is working on a WASI runtime as well. But yeah, Cloudflare has a similar thing, but it's not using WebAssembly. Or it uses V8 to load WebAssembly, so it's a similar thing. But it's not as bleeding edge or cool, I think. I think WASI is really cool. And so as I was saying, WASI is something that they're working on, maybe bringing to Go 1.14. So Go 1.13 was just released, and there's like 2.5 months left of this release window or whatever. So if they manage to get the WASI compile target in before December or whatever, then we might see WASI in 1.14, which would be really exciting.
All right, thank you. Any more questions? Alrighty, I think you've already chosen the best,
Yes,
best
please.
question, right? Come here. Tell us a little about yourself and why you asked that question.
Okay, thanks. Hi, I'm Boris. I'm a junior Go developer at OzoneTech, and I'm also like looking around for other technologies and front end as well. So that's why I was interested in this presentation in this topic. I asked it because 10 megabytes is a lot, isn't it?
Yeah.
All right, thank you. Here's your book. And thank you, Johan, for amazing talk. Thank you.
Thank you.